So in this video, I'm going to go through the assumptions required for op-amp analysis, and then I'm going to apply it to an example related to this op-amp system here. So to start off with, we have an assumption that the op-amp draws zero current. So if we look at our system, this here is the symbol for the op-amp, and we can see it has two inputs on the left here. One is positive and one is negative, and it has one output. So if we're saying that the op-amp draws zero current, that means we have to assume that the current in through this terminal and the current in through this terminal is equal to zero. So I'm going to mark it on the diagram. I'll call this one IA, and I'll call this one IB, and both of them are going to be zero. So moving on to the next assumption, we're saying that under external feedback, voltage difference between input terminals is zero. So this part here represents the feedback section. So we have some input, it gets fed through the op-amp and things happen in here. And then we have an output, which is then fed back to the input. So this here is the feedback. So we definitely have this case of external feedback. And what we're saying is that voltage difference between input terminals is zero. So the voltage here and the voltage here have to be the same. So the voltage in all this part is identical because there's no components to change the voltage over. So let's just pick this node down here and mark in, call it V1. Again, all of this is the same because there's nothing to change the voltage through there. I'm going to call it VG though. And for this assumption, both of those are going to have to be equal because that means there's no difference. So now I'm going to move on and apply it to an example. So what I'm going to do is solve for the transfer function, which is V out divided by V in. So what we're going to find for this is that we're going to use nodal analysis. It's the easiest way to get your transfer function. So for nodal analysis, what you're looking at is the current into and out of a node. So the node that we're going to pick is the one where I've drawn like this V1 at. The reason is, at this point we should be able to relate in the voltage V in through this component, and we should also be able to relate in V out through this component. So that's what we want in the equation so that we can rearrange it to look like this. So I'm going to mark in some directions for the current into and out of the node. So I'm going to assume that this is going in since this is the input terminal. And I'm going to call it I1. And we have to pick a direction for this. I'm going to assume it goes out here, so I'm going to call it I2. So the equation we need to satisfy is that the sum of the currents at this node are equal to zero, which means that current in equals current out. So going in, we have I1, and we have 2 going out, so I'm going to make them both negative since they're the opposite direction, and it has to be equal to 0. Now at this point we can simplify our equation a little bit based on our assumptions. So IA, we said before that from our first assumption here, has to be equal to 0. So that immediately gets dropped from our equation. So now what we need to do is instead of representing this in terms of I1 and I2, we need to get it in terms of V out and V in. So how we can do that is that we have a relationship where voltage is equal to current multiplied by the impedance. And if I rearrange this, current is equal to voltage divided by impedance. So I should be able to replace each of my currents here in terms of the voltage and impedance. So let's start by looking at I1, and we can say that we're going to have a voltage drop across this component, which is going to be equal to the voltage, so V in minus V1. And this gets divided by the impedance. So the impedance of this one is Z1. Alright, so now let's go ahead and look at I2. Okay, so the voltage drop across this component is going to be what we started at, which is V1 minus what we end up at, which is V out, and it gets divided by the impedance, which is just Z2. There's a minus in here which gets carried down, and it's equal to 0. Now we can use our second assumption to simplify our equation. So our second assumption is that V1 is equal to Vg, so these two are equal. And what we know from looking at this diagram is that Vg is basically going to be the ground voltage since they're connected together. And we know that ground is considered to be 0. So if Vg is equal to 0, V1 is also going to have to be 0 from this relationship. So we can get rid of both of these terms. So all that we're left with C2, sorry, is this, and if you rearrange it for V out divided by V in, you end up with negative Z2 on Z1. So this here is the final answer for our relationship between the input and output voltages. And this is known as an inverting amplifier. The reason it's called inverting is because we get a negative on here, so it flips over the relationship. And we can see that it's just the ratio of the two resistors that you have in your system, so Z2 and Z1. So that's all there is for this question, and see you in another video.